Hi there, we have arrived in our physics course to a place where we are going to be starting discussing um, forces in 3 dimensions. So there will be several, up to 3 forces now acting in 3D, and I would like to discuss with you or teach you how to use proper um, vector notation in 3D, because when you're going to be submitting your work, often you'll be drawing pictures, and picture that you'll be drawing on a 2-dimensional paper needs to show 3 dimensions. So here is just a short video about vector notation. When we want to show outgoing or ingoing vector into a paper, we use an arrow notation. So I have an arrow here to show you, and if this arrow is going toward you, right, like this, you see sort of like a point. You see the tip of the arrow. So to show that on a paper, we use a notation like this. So this would mean a vector, an arrow, is coming out of the paper towards you. On the other hand, if you want to show a vector that's going into the paper, you would, we sort of use what we see when a vector is going in, like this. And this is the standard notation to show that. So this would mean that this black vector is pointing into the paper. So you're sort of looking at the end of the vector like that. And here are some examples of how this might look. So here on this picture, you can see a particle, the yellow particle in here, is moving at the velocity showed by this vector. Okay? And it's moving in a magnetic field, and this magnetic field of intensity B is directed in a perpendicular direction to the plane of the paper, and you can tell that from this notation, from these x's, that the vectors of the magnetic field are going into the paper, If they were coming out of the paper, so towards you right now, it would show a point like that. But since the intensity vectors showing the intensity of the magnetic field are going in, then we show the axis. And you can sort of tell that this is a uniform magnetic field, so the axes are uniformly spaced one from each other. So uniformly spaced uniform magnetic field. Here are some more examples how this notation can be used to be more clear on a 2-dimensional paper. Let's talk about magnetic field around a current carrying wire. So if I have a wire that shows the current going up, by the way, remember that if current is shown up, the electrons are actually moving the other way, so the electrons will be moving down. For historical reasons, Benjamin Franklin, he postulated that the electrical current is motion of positive particles because electrons were not discovered at that time yet. Anyway, just a quick side note. So if current is shown going up, the electrons are actually moving down. This is important when you're going to be using the palm rules, for the second right-hand rule. Anyway, so if I wanted to show how the magnetic field generated by this electrical current in the wire looks like, there are several different ways how I could do it. For example, I could show it like this. Okay, so it has a form of concentric circles, and we would use the first right-hand rule to show whether the circles go, clockwise or counterclockwise. And so you would place your thumb pointing in the direction of the electric current, and then your curved fingers are showing you the direction of the magnetic field. However, some people might misinterpret this picture. There are certain weaknesses to this type of notation. By the way, notice that the field lines are spaced more closer to the current, closer to the conductor, and they are spaced. drawn further apart from each other as we go further away from the wire, just to show that the magnetic field there is weaker. Okay. So here is an alternate notation how we could show this using the arrow notation. It would look something like this. So on one side of the wire, again it's showing the same thing. Okay. On this side of the wire here, the magnetic field lines are going into the plane of the paper, and on the other side, they're coming out. So on this side they're going into the paper, and on this side they're going out of the paper. And again, notice that here these two are closer to each other than these two, showing that the further away we go from the wire, the weaker is the magnetic field. I hope that this notation makes sense. Using the into the paper and out of the paper vectors. If you have a hard time understanding this notation, just give me a quick Skype call or email to me, and I'll Skype call you, and let's get going so you can finish all of your assignments on time.